Hi all. This topic is about microwave tubes. One of the type is magnetron. So, in this topic we are going to discuss about magnetron. So, what is magnetron? Why it is? So, it is a device that generates higher power electromagnetic wave, and it is basically considered as a self-excited microwave oscillator, and it's also known as crossed field device. So the reason behind calling it so is this, that the electric and magnetic field produced inside the tube are mutually perpendicular to each other. Thus the two crosses each other. And the operating principle, it is basically a vacuum tube of high power having multiple cavities, and is also known as cavity magnetron because of the presence of anode in the resonant cavity of the tube. The operating principle of a magnetron is such that when electrons interact with the electric and magnetic field in the cavity, then high power oscillations get generated. Magnetrons are majority used in radar as being the only high power source of RF signal as the power oscillator despite a power amplifier. So a cylindrical magnetron has a cylindrical cathode of a certain length and radius present at the center, around which a cylindrical anode is present. The cavities are present at the circumference of the anode at equal spacing. Also, the area existing between the anode and the cathode of the tube is known as interaction space or region. And it is to be noted here that there exists a phase difference of 180 degree between adjacent cavities. Therefore, cavities will transfer their excitation from one cavity to another with a base shift of 180 degree. And this construction is continuing, then we can say that if one plate is positive, then automatically its adjacent place will be negative. And this is clearly shown in the figure, the previous slide. More specifically, we can say that edges and cavities show 180 degree phase apart relationship. As we have already discussed that here the electric and magnetic field are perpendicular to each other, and the magnetic field is generated by using a permanent magnet. Okay, so that working of magnetron, here the excitation to the cathode of the magnetron is provided by a DC supply which causes the emergence of electrons from it. So here in this section we will discuss the working of magnetron under two categories. First, without applying the RF input to the anode, and the second one with the application of RF input. So first case is when RF input is not present. That time when the magnetic field is zero or absent. When the magnetic field is absent, then the electron emerging from the cathode radially moves towards the anode. So this is shown in the below figure, and it's so because of the moving electron does not experience the effect of the magnetic field and moves in a straight path. So this is the absence of magnetic field. And case 2 is when a small magnetic field is present. So in this case, small magnetic field exists inside the magnetron, then the electron emerging from the cathode will slightly deviate from its straight path, and this will cause a curvy motion of the electron from cathode to anode as showing in the below figure. This motion of the electron is the result of the action of electric as well as magnetic force over it. And the case 3 is in case when the magnetic field is further increased, then electrons emerging from the cathode gets highly deflected by the magnetic field and graze along the surface of the cathode, and it's shown in the below figure. This causes the anode current to be zero. So the value of the magnetic field that causes the anode current to become zero is known as the critical magnetic field. And if the magnetic field is increased beyond the critical magnetic field, then the electron will bounce back to the cathode itself without reaching the anode. Okay, so the reaching of the emitted electrons from the cathode back to it's known as back heating. So to avoid this, the electric supply provided to the cathode must be cut off after oscillations have been set up in the tube. And the second major case is when the RF field is present. So in case an active RF input is provided to the anode of the magnetron, then oscillations are set up in the interaction space of the magnetron. So when the electron is emitted from the cathode to anode, then it transfers its energy in order to oscillate. Such electrons are called favored electrons. In this condition, the electrons will have a low velocity and thus will take a considerably high amount of time to reach from cathode to anode. And here the case 2 is another condition arises in the presence of RF input. In this case, the emitted electron from the cathode while traveling takes energy from the oscillations, thereby resultantly increasing its velocity. So despite the reaching the anode, the electrons will bounce back to the cathode and these electrons are known as unfavored electrons. And here the case 3 is the R of input is further increased than the electric electron emitted while traveling increases its velocity in order to catch up the electron emitted earlier with a comparatively lower velocity. So all those electrons that do not take energy from the oscillations for their movement are known as favored electrons. And these favored electrons form electron bunch or electron cloud and reaches anode from the cathode. So the formation of electron bunch inside the tube is known as phase focusing effect. Due to this, the orbit of the electron gets confined into spokes. These spokes rotate according to some fractional value of electron emitted by the cathode until it reaches anode while delivering their energy to oscillations. However, the electrons released from the region of cathode between the spokes will take the energy of the field and get back to the cathode very quickly. But this energy is very small in comparison to the energy delivered to the oscillations. So the movement of these favored electrons inside the tube enhances the field existing between the gaps in the cavity. So this leads to sustained oscillations inside the magnetron, thereby providing higher power at the output. So next we need to know about what is frequency pushing and pulling. So the variation in the oscillation frequency of the magnetron gives rise to the term frequency pushing and pulling. When the voltage applied at the anode of the magnetron is varied, then this causes the variation in the velocity of the electrons moving from cathode to anode. This resultantly changes the frequency of oscillations. Therefore, we can say when the resonant frequency of the magnetron shows variation due to the change in the anode voltage, then it is known as frequency pushing. The change in resonant frequency is sometimes a result of the change in the load impedance of the magnetron. The load impedance varies when the change is purely resistive or reactive. This frequency of variation is known as frequency pulling. So, what is the advantages from magnetron? So, magnetrons are highly efficient device used for generation of the higher power microwave signal, and it is used in radar, can produce radar system of better quality for tracking purpose. It is usually in small size, thus less bulky. And disadvantages are it is quite expensive. Despite producing a wide range of frequency, there exists a drawback in controllability of the generated frequency, and it offers a average power of around 1 to 2 kilowatts, and it is quite noisy. And these are the applications of magnetron. It's a major application in a pulsed radar system in order to produce a higher power microwave signal, and it is used in heating appliances like microwave ovens so as to produce fixed frequency oscillations, and tunable magnetrons find their applications in sweep oscillators.